Hello everyone. Today we'll be solving a problem that came in GATE 2016 in one of the three sets from analog electronics. So in the problem it is given that in the circuit shown there are two Zener diodes Z1 and Z2 that clamp the output voltage to either plus 5 or minus 5. And it is given that the switch is initially closed and it is opened at time t equals 0. So there are two cases. One is before the switch is closed and then it is when it is opened. So first of all, we look at the circuitry given over here and analyze it separately and get the key takeaways that we can use to solve the problem. So this is an excerpt from a book and we have the same circuitry of the Zener diodes over here. So when the value of Vi is positive, what will happen is Z1 will conduct and it will be a battery of 0.7 volts and Z2 will be in breakdown, so it will also be a battery but of VZ2. So the value of the output will be VZ2 plus 0.7. And when V1 goes negative, what will happen is Z2 will conduct and it will be a battery of value 0.7 volts and Z1 will be in breakdown and it will also be a battery but of VZ1 volts. And VO will be equal to minus of VZ1 plus 0.7 as it is given over here. So it is basically a clipper circuit which clips the value of higher values of Vi to this value and the lower values of Vi to this value and passing all those with slope equals 1. Okay. So with this knowledge of this particular circuitry, we move forward to solve the problem. So first of all, we'll analyze the initial situation when the switch is closed. So when the switch is closed, okay, so we have S as closed. This is S and this is initially closed. So when this is closed, this cap is a short, so it is no longer in the picture. And since this is a short, if this is 10, this is also 10. So we have the potential of this node as 10 volts. Now let us assume that the potential here is, see, the thing is the op amp will not act like a virtual short due to the circuitry given over here. Okay, so the reasoning for that I'll provide it, but I'm just telling you that it will not be in virtual short, so we cannot take the voltage here as 10. So the voltage here will be either plus Vsat or minus Vsat. So first of all, ignore that this is 10 and assume that this is 10 volts. Okay. What I wish to do is, given this voltage, I need to tell you what will be the value of this voltage. Okay. So let us assume that this is 10 volts. That is plus Vsat. So the voltage at this node, let us assume that it will be minus 5. See, it can be any one of these two things. Either it will be plus 5 or it is minus 5 as per the question. So let us assume that it is minus 5 for the time. Now what will happen is, since this is minus 5, this will be minus 1. And the current that is flowing over here will be in this direction and it will be equal to 1 milliampere. And the current that is flowing in this resistor will be in this direction. So the net current will flow in this direction. This is minus 5. Okay. So if this is minus 5, then as I mentioned above, when Vi is negative, Z2 conducts. And if Z2 conducts, it must flow current in this direction. But to satisfy case here at this node, the current is flowing in this direction. So this is an ambiguity, or rather our assumption is incorrect. So the value of the potential at this node is not minus 5. So it has to be plus 5. I'll just cross check for you whether the plus 5 satisfies the condition or not. So if this is plus 5, what will happen is there will be the current that will be flowing in this direction and the magnitude of the current will be 10.6 milliampere. And there will be this current, but it will now be flowing in this direction. And if this is 5, this will be 1 and the value will be 1 milliampere again. So now what will happen is the current to the Zener diode will be in this direction and the magnitude will be 9.6 milliampere to satisfy KCL at this. Okay, but this is now in agreement with the assumption that this is 5 volts, because if this is 5 volts, as we discussed here, Z1 will conduct, and if Z1 conducts, it must flow current in this direction, and it is satisfied because the 9.6 milliampere that we calculated is in the same direction and it allows Z1 to conduct. Similarly, you can cross check yourself that when this is minus 10 volts, this is minus 5 volts. You can assume it to be 5 volts, then do the same analysis that I did here. And then you can contradict that assumption and get to the result that when it is minus 10 volts, the potential at this node is minus 5 volts. Okay, so now we have figured out this much. Now we wish to figure out what will happen when the switch is closed. So this is 10 volts. So assume that the voltage here is minus 10 volts. Let's say the voltage here is minus V sat. Then here it will be minus 5 as I mentioned earlier. This will be minus 1. Now this is minus 1 and this is 10. V minus is higher, which means that this minus 10 assumption is correct. Okay, what if we had assumed it to be plus 10? If we had assumed it to be plus 10, this would have been 5 and this would have been 1. So this is not possible because at minus we have 10 and at plus we have 1. So this assumption is incorrect. So our earlier assumption was correct of this potential being minus 10. So this being minus 5 and this being minus 1. Okay, this satisfies because the potential here is 10. So this will be at minus V set. Okay, so this is when S is closed, which is previously to the operation that is opening the switch. So we have analyzed this very carefully, and now we wish to analyze the latter case when S is open. So S is open at t equals 0 plus, and we wish to analyze what happens then. Okay, so when S is open, this voltage initially remains at 10 volts itself, and then what happens is due to this current that is flowing here, this capacitor gets charged, and this will get charged in this direction. So at steady state, we'll have this voltage to be minus 10 because the capacitor becomes an open circuit. While at t equals 0 plus, this will be 10 because the capacitor acts as a short circuit. So let's say this node potential is X. We can say that voltage at position X at t equals 0 plus is 10, and voltage at position X at t equals infinity is minus 10 because the cap is an open circuit and this is minus 10. Okay, so now what we are asked in the question is the time t equals t1 in seconds at which VO changes state. VO is this. So initially, what is the state of VO? It is minus 5. Now, why will VO change its state? That is the first possible question. So let me answer it. What happens in the steady state is this node potential becomes minus 10 volts. And this will become 10 volts, this will be 5 volts, this will be 1 volts. I got to this potential in the same way. You can take the other way around and then contradict them and do all the story that we did above to get to this picture. Okay, so now we have this. So this potential is 1 here, but earlier it was minus 1. So this is the picture in the steady state. So in the steady state, VO has changed its state to 5 volts as you can see here. So they are asking what will be the time in seconds at which VO changes state. I mean, there will be some time in between this and this. So they are asking about us that about the trip point. Okay. So about the trip point, or when the point at which the point of time at which VO changes state, that we wish to calculate. So when will VO change state? See, VO is changing state because of this reason. See, this is an op amp. This is an ideal op amp. This voltage is 10 volts. The potential at this node goes from 10 volts to minus 10 volts. Okay, so when it is at 0 volts, still the negative potential is at higher end as compared to the positive potential, and this remains at minus 10. But what if it goes to minus 2 volts? Then this will be lower and this will go to plus 10, and we will reach to somewhere over here. Okay, and VO will change state because for this to be 10 volts, this is 5 volts as we already discussed. So what is the trip point? The trip point is when this node potential is minus 1 volts. Because if this node potential is minus 1 volts, then it matches with this. And just as it becomes minus 1.001 volts or whatever, then this becomes plus 10 and this becomes plus 5 and VO changes state. Okay, so the trip point is minus 1 volts. That is, VO changes state when the potential at this node becomes minus 1 volts. This is the trip point. Okay, so this was the most difficult part of the problem to find out that when this node potential become minus 1 volts, then we have the VO changing state and this becomes minus 10 to plus 10. This goes to plus 10, this goes to plus 5, this goes to 1, and the story continues. Okay, so even if, let's say what happens is this goes to, let's say minus 2, then this goes to plus 10, this goes to plus 5, this goes to plus 1. So this is not a problem because this is plus 1 volts and this is minus 2 volts. The positive end is higher, being at plus 1, and this is at minus 2. So this being 10 volts is justified. So it is not that the steady state is wrong. The steady state is equally satisfied. So the main uh, thing was that this is minus 1 volt. This was the main conclusion that had to be drawn. So knowing this, this becomes a simple RC circuit problem where you have a simple RC network because the op amp does not load. There is no current flowing here, so it is a simple RC network connected by battery of 20 volts. And we wish to calculate when this node potential goes from minus 10 to 1 minus 1 volts. And this is a fairly easy problem. The time constant of the circuit is 1 second, and you can easily use the equation. I mean, this is not something very extraordinary because the initial value was 10, so the natural response decays and the forced response is like that. You can equate it to minus 1 and you can find out the value of 10 as ln 20 by 9, which gives us the value of time as 0.798 seconds, which will be the answer to the problem. So the main thing was the trip point is when the voltage at the node X becomes minus 1 volts. Okay, so the answer to the problem will be 0.798 seconds. So in my opinion, this was a very good problem, and it involved good understanding of Zener diodes, basically this circuitry, which clamps the output voltage and makes this op amp operate in saturation region, and basically clipping and clamping. And the most important thing was to realize that when this is 10 volts, this is 5 volts, and when this is minus 10 volts, this is minus 5 volts. This was the most important piece of information that had to be realized. So yeah, that was about it. And then it was a simple RC circuit, which was fairly easy to solve. So I hope that you like the solution of the problem, and this is my point of view of the problem. So yeah, thank you for watching, and stay tuned for upcoming videos. Thank you.